Second goal for this particular day, horizontal asymptotes, or I'm actually going to say non-vertical ones is really what it's going to come down to. Horizontal asymptotes. We've done a bunch of problems here. In each of these problems, numbers 1, 2, 3, and 4, and you'll notice what we wrote on problem number 1. If we take the limit as x approaches infinity, that's how we find horizontal asymptotes. And we've done this already. So this problem number 1 would have a horizontal asymptote at y equals 5. This problem number 2 would have a horizontal asymptote at y equals 2. Problem number 3 would have a horizontal asymptote at y equals 0. Problem number 4 would have a horizontal asymptote at y equals infinity. I don't know that that makes sense. We're going to come back to that problem. Let's look at this problem number 5 instead. So this one specifically, instead of saying take a limit, this one says find horizontal asymptotes. Well, the way you do that is you take the limit as x approaches infinity. Well, if I take the limit as x approaches infinity, now it looks just like the problems we were just doing. So same scenario. Locate the highest power of x in the denominator. Well, the thing that gets a little tricky about this one is you got a square root with it, because we look at it and we go, oh, x squared is the highest power, but we've got a square root on it. So what does that mean? It looks like the highest power of x in the denominator would be x to the first. Okay, so we'd like to multiply top and bottom by 1 over x. Well, that makes sense in the numerator, because the numerator then, well, let's see, that numerator would be limit as x approaches infinity of 3 plus 1 over x. The denominator gets tricky, though, because if you try to multiply a square root of 2x squared times a 1 over x, you can't multiply them because they don't both have a square root on them. So what we're going to have to do is we're going to have to get a little bit creative here, because instead of multiplying the bottom by 1 over x, let's get creative. Let's call it the square root of 1 over x squared. Because if I multiplied by the square root of 1 over x squared, first off, it would still be equivalent to what we multiplied the numerator by, which makes sense. And it puts it in the format that makes more sense here, because a square root times another square root, well, the x squareds are going to drop out. Square root of x, or the square root of 1 times the square root of 2 would give me the square root of 2. Or let's just call it the square root of this whole thing, and then we'll deal with sorting out the square roots in a second, because we're about to take this, this 1 times the 1 over x squared, and if we got the square root over the top of both of them, then this becomes a plus a 1 over an x squared. And so if we now look at this thing and we evaluate this limit, again, same deal. Anybody who's got an x in its denominator is effectively going to drop out. Well, what do we have left? What we have left is a 3 over a root of 2. So what we found is that this function has a horizontal asymptote at y equals 3 over the square root of 2. 3 over the square root of 2. Nice. Now here's the tricky thing. I'm going to put a little star up here because this is going to be kind of a big deal. Horizontal asymptotes, if we have a square root in the problem or an absolute value in the problem, we've got to make sure that we also check the limit as x approaches negative infinity 2. Okay, so we've got a square root in this problem, so what we're going to have to do is we're going to have to also, in this problem, do the limit as x approaches negative infinity of that 3x plus 1 over the square root of 2x squared plus 1 and see what happens. Well, we've got the same exact issue that we had a second ago. We're going to multiply the top and the bottom by 1 over x and the square root of 1 over x squared. But this is where it gets a little bit tricky. It seems like it's actually going to work out pretty well, but the place that it gets tricky here is that these two things that I just wrote down, these two things are not equivalent. We're talking about x is headed toward negative infinity. Because if you think about negative numbers, if you put negative infinity into this top one, you're going to have 1 over a negative number. If you put negative infinity into this bottom one, you're going to have 1 over a negative number that gets squared and is inside of a square root. Well, a negative number squared is going to turn out positive, so you've really got the square root of 1 over a positive number And when you take that, that was, again, being squared, so when you cancel the square root and the square out, you're going to end up with a positive value here, where we ended up with a negative value here. So in order to make those two things match, we're going to have to put a next sign on one of them. It doesn't matter which one. Let's say that we decide to put a negative here. If we did that, that'll change this to a positive. That'll match this positive. The tricky thing about taking limits as x approaches negative infinity is that the square roots and the absolute values kind of mess up your values. So that's why we have to check them both. Now, if you check them both, the only thing that's going to turn out different after we carry out the limit, and I'm going to refer back to everything that we did up here because it's going to work exactly the same way. The only difference in the result is this result is going to end up with a negative in front of that 3 over root 2. So why is that? It's because of what's in green. But what we have found is this thing, not only does it have a horizontal asymptote at y equals positive 3 over root 2, but it's also got one at negative 3 over root 2. So when we deal with horizontal asymptotes, if you have a square root or an absolute value, you've got to make sure that you check both positive and negative infinity. Well, in effect, checking negative infinity, all it does is it changes the sign on what you got for positive infinity. So that's kind of a nice little shortcut to have there. Going back to this previous problem, this problem number 4, this problem actually doesn't have a horizontal asymptote. This one actually has an oblique asymptote. This one has no horizontal asymptote because if we wanted to say it would have one at y equals positive infinity, well, that doesn't exist. So this one actually has an oblique asymptote. Oblique being a fancy word for diagonal, and if you want to find out how to get it, you actually go back to the original problem and you actually do the division. So I'm a fan of synthetic division because we're taking x squared plus 1 and we're dividing it by x plus 3. Well, that would be long division. If you wanted to do long division, we certainly could. Well, let's see, we would actually have to leave a little space here because we don't have an x term in there. So what are we going to have to multiply by? Well, here we're going to have to multiply by an x. So x times x is x squared. X times 3 is 3x with a positive sign on it. When we subtract everything, we'll have negative 3x plus 1. Well, what do we have to multiply by? Well, let's see. Now we're going to multiply by a minus 3. If we multiply by a minus 3, that'll give us a negative 3x here. And negative 3 times 3 would be negative 9. When we subtract, we change signs. So here's going to be a 10. That 10 would be your remainder. So here's what we've just found. We just found that after dividing this thing, we ended up with a result that was y equals x minus 3 with a remainder of 10 over an x plus 3. So there's how your official division. We did it the long way. If you want to do synthetic division, you certainly could. It would have saved you a little bit of time probably. But what we do here is we divide and we toss out the remainder, and this is your equation of your oblique asymptote. So this one would have an oblique asymptote at y equals x minus 3. I don't expect you to do that very many times. It's not a huge priority for us, but I want you to know what happens when a function's supposed to have a horizontal asymptote, but actually we end up with an infinity result. You do the division, whatever you have as a result is going to be your oblique asymptote, providing the result comes out to be the equation of a line. If the result comes out to be the equation of anything else, you don't have an oblique asymptote. So there's your horizontal asymptote with a little extra added in.